Here in our first 321 lecture video, we're going to talk about diode basics along with the basic operation of a diode. So first of all, in order to fabricate a diode, you just put together two pieces of semiconductor, okay, where one semiconductor is p-doped and the other semiconductor is n-doped. And we call this a p-n junction, okay, where the p and the n material meet. And whenever you have a single p-n junction, you have a diode. Okay, now, as we'll talk about, the most common type of semiconductor that's used to make diodes is silicon because it's so abundant. But other semiconductor materials that are often used in electronics are gallium arsenide and also germanium. But by far, silicon is the most popular of all the semiconductors. Now, just like in circuit theory, we had symbols for all the different circuit components in a circuit. Well, in electronics, we also have symbols for all the different electronic elements, such as a diode. And the diode circuit symbol looks like this. Okay, where the arrow of the symbol corresponds to the P side, and this line corresponds to the N side of the junction. Now, some terminology that you need to know is that the P side, or the arrow side of the symbol, that's called the anode, and the N side, or this line of the symbol, that's called the cathode. And we often abbreviate anode with capital A and cathode with capital K. We use K instead of capital C because capital C is for capacitance. Now, a physical diode will always have a marking that indicates the cathode side. So, for example, if you have a diode shaped like this, there'll be a band or some sort of marking on one side, and wherever that marking is, that's the cathode, and therefore the other side's the anode. Alright, so that's just some basics about diodes. Now, let's go over the basic operation of a diode. So, let's say we have a diode and it's part of some circuit. So, I'm not showing the entire circuit here, it's just focusing on the diode that's part of a circuit. Well, while in that circuit, the anode side, okay, remember this is the anode side, this is the cathode side. Well, if when in that circuit, the voltage on the anode side of the diode is greater than the voltage on the cathode side, current will flow through the diode. Okay, and the current that flows through the diode will flow anode to cathode because, as you learned in 201, current flows from the higher side to the lower side through components that are absorbing power. And just like a resistor always absorbs power, a diode always absorbs power. So it's going to flow from the higher voltage end to the lower voltage end, as we see here. Now, ideally, the amount of voltage across a diode when current is flowing anode to cathode. And by the way, when we have this condition, it's called forward bias. Okay, when current is flowing anode to cathode, we call that the forward bias current. And ideally, when the diode is forward bias, allowing current to flow anode to cathode, the voltage across the forward bias diode, okay, sometimes you'll see the subscript FB for forward bias, but in our book, the author chooses to use gamma. So V gamma, that's the forward bias voltage. Well, ideally, that voltage is 0 volts. And ideally, it's 0 volts for any amount of current. Okay, so for any amount of diode current or forward bias current, the voltage across that diode will be 0. Well, if you remember from your circuit theory, this is the same voltage current relation as that of a short. Okay, a short will have 0 volts across it no matter how much current is passing through it, just like an ideal diode that's forward biased. So we'll say that ideally a forward biased diode acts like a short. Alright, and we say it acts like a short because it has the same voltage current relationship that a short does. Now in actuality, when a diode is forward biased, there will be some voltage dropped across it, and the amount of voltage that's dropped across it primarily depends on the material, the semiconductor material that the diode is made out of. So for example, if it's a silicon diode, it's going to drop between 0.6 volts somewhere between 0.6 and 0.7 volts will be the forward bias voltage if it's silicon. If it's germanium, it's less than that. VFB for germanium is in the range of a couple tenths of a volt to 0.3 of a volt. Okay, and if it's gallium arsenide, it's about a volt or so. Now, of these, like I mentioned earlier, silicon is the most popular. So in this class, we focus on this one, and this one you might want to remember. Okay, so we'll talk more about the actual case and why you get this this amount of voltage drop across an actual forward bias diode. But this first lecture is just an intro, and we'll get into more detail on this later on in the course. Alright, so you could also have that same diode in a circuit where you have the opposite, where now instead of the anode voltage being greater than the cathode voltage, it's the reverse, that the cathode voltage is greater than the anode voltage. Again, this is part of a circuit. Okay, well, when you have this condition, ideally no current passes through the diode. Okay, the diode will not allow current ideally to pass through when the cathode voltage is greater than the anode voltage, and there'll be no current. Okay, and this is called the reverse bias condition. Okay, remember when current is flowing is flowing from anode to cathode, we call that forward bias. This is reverse bias, and ideally that diode that's reverse bias will not allow any current to flow through for any voltage. Okay, so for any reverse bias voltage. So, VK could be just a little bit greater than VA, or VK could be a whole lot greater than VA. And ideally no current's going to pass through that diode. Well, no current for any voltage, that's the same current voltage relationship as an open circuit that you learned about in circuit theory. So we say that ideally a reverse bias diode acts like an open circuit. Okay, acts like an open. Now, in actuality, there'll be a small amount of current. Okay, very tiny. Probably at most microamps, and a lot of times, less than that. Oops. Sorry about that. It should be very tiny. Okay, the current in actuality is very small. Like I said, at most microamps. And in a lot of applications, you're not going to worry about that small amount of reverse bias current, and for all practical purposes, you can just say it's 0. So really, when you take a look at the basic operation of a diode, you can make a summarizing statement that basically a diode is a voltage-controlled switch. A voltage-controlled switch. Right? Because as we saw, when it's forward bias, it allows current to flow, virtually unimpeded, ideally unimpeded. So here, when it's forward bias, the diode's acting like a switch that's on. Okay, because it's allowing current to pass through. And that's due to this relationship between the voltage on each end, the anode and cathode end of the junction or the diode. Whereas if I simply just reverse that voltage and make the cathode greater than the anode voltage, well, now it's not allowing any current to pass through, and that's like a switch that's off. Okay, so really, you know, you can summarize diode, the basic operation of diode, of that of a voltage controlled switch. And the last thing we'll talk about in this video before we do some examples involving diodes, some circuit analysis involving diodes, is that we can take our basic operation that we just talked about and summarize it in what's called the ideal diode model. See the ideal diode model, here's our circuit symbol of the diode, and then the voltage across the diode is defined such that the anode side is the higher voltage end of the difference. Okay, so VD, which is the voltage across the diode, given this definition of polarity, would just be VA minus VK. Well, if that voltage difference across the diode is greater than 0 or equal to 0, that's the forward bias case that we talked about, and ideally the diode acts like a short. And if we have the reverse case, where the cathode voltage is greater than the anode voltage, therefore VD will be less than 0, well, that's the reverse bias situation, and that's when the diode acts like an open. So this ideal diode model just summarizes the basic operation that we did on the previous 2 pages. And we're going to use this model to help us analyze circuits with diodes in them where we treat the diodes as ideal. And we'll start that in the next video.